My mouse cannot move over for the, got it. I need to exit.
Okay, we are on YouTube now. So let me start with a brief introduction. So today we are very happy to invite Dr. Yixiang Deng to give a presentation on a research frontier of diabetes modeling. So Dr. Yixiang Deng is currently a postdoc associate advised by Professor Garnet Alter at Ragon Institute of MGH, MIT, and Harvard. And she is also co-advised by Professor Douglas Norfenberg at MIT. So prior to joining the Alternap, she received her PhD from the School of Engineering at Brown University in 2021, working with Professor George Kinetics. Dr. Deng received her bachelor degree of engineering from School of Levy Architecture, Ocean and Civil Engineering at Shanghai Jiaotong University in 2015. So her current research interest is on computational system serology for infectious disease, including the type 2 diabetes. So Yixiang, please start your seminar, and later we will follow up with a Q&A.
Okay, thank you, Jen, for the kind introduction. Hi, everyone. I'm Yixiang Deng. It's my honor today to present some of my work supervised by Professor George Kinetics during my PhD study on biomechanistic and bioinformatics modeling for diabetes. Before we go to the science part, I want to introduce some of the diabetes-related common knowledges. According to the statistic in 2020, there are more than 34 million of Americans having diabetes, and the number goes up to 88 million for people having pre-diabetes. This has resulted in a huge burden to the healthcare costs for Americans with diabetes by go beyond doubling the healthcare costs for the patients, and also causing a large cost, annual cost for the patients in America. These statistics show that diabetes is a prevailing epidemic, but on the positive side, we acknowledge that there is a lot of medical data for diabetic researchers. On the other side, it is understood that certain groups of people are more susceptible to diabetes, depending on the demographic data like age, sex, and race. Additionally, lifestyles and medications are crucial to the management of diabetes as well. Luckily, with this developing of bioinformatic techniques and abundant medical data records, we can underscore the risk factors in diabetes and help patients develop a better lifestyle. So, and some background about diabetes is that it is a group of diseases characterized by really high blood glucose levels, greater than 180 milligrams per deciliter, that result from either the defects of the body's ability to produce and or use insulin. In general, diabetes is characterized into 3 different types. One of them is type 1 diabetes, usually occurs in the early age of life, taking up 10% of the diabetes cases, while type 2 diabetes is believed to be more associated with obesity and aging, taking up 90% of the cases. Another type is more transitional, which usually happens to pregnant women. Is called the gestational diabetes, and the prevalence is about 10% during pregnancy. People with diabetes are often advised to take more exercises, maintain a healthy diet, and taking glucose lowering drugs. However, intensive exercise, strict diet control, and additional glucose lowering drugs may increase the risk of hypoglycemia, where the patient's blood glucose level drops below 70 milligram per deciliter. If hypoglycemia are not handled carefully, dangerous a consequence is leading to a coma for the patients. In the consequence level, we identify that both hyperglycemia and hypoglycemia are dangerous to patients' vascular integrity in several ways. For the pathological damage due to diabetes usually starts from the changing in the biochemical and biomechanical properties. For example, the abnormal cell receptors and increased protein concentrations in patients' blood sample, and also leading to like abnormal cell-cell interactions. All these changes lead to very severe pathological states, such as chronic inflammation, abnormal blood coagulation, and thrombos formation. If not treated properly and timely, these abnormal changes in blood will result in the following microvascular diseases, and the worst is the cardiovascular diseases. Compared to patients without diabetes, patients with type 2 diabetes were proven to be more likely to die from cardiovascular diseases. Therefore, it is of very great importance to understand the mechanism of the altered blood mechanics and the fluid dynamics to benefit the drug design for patients who have already developed these complications. So I'm going to show the overview of my talk today. In part one, I'm going to introduce some of my work on fibrinogen-dependent red cell aggregation and hemodynamics in thrombos formation. For the second part, I'm going to show the data-driven modeling I developed for glycemic prediction, including short-term glucose prediction using deep learning and also long-term hypoglycemia detection. So part one is about mechanistic modeling. So here is the problem setup that we focus on. Under physiological conditions, the linear stacking of red cells will form a chain-like structure, namely the rouleau. Although rouleau formation is reversible in the normal blood, the hyperaggregatability of the red cells in diabetic blood leads to persistent long rouleaus, and this increases the blood viscosity, which is really harmful to the surrounding tissues and organs. In this work, I will present our experiments and simulations on red cell aggregation using microfluid channel mimicking the capillary network shown in these slides. So inspired by this in vitro experiment performed by our collaborator at MIT, we found that the normal blood with a lower fibrinogen level seldom have red cell aggregation, as shown in this cartoon in this movie, while the diabetic blood with high fibrinogen level shows longer and persistent rouleau. We identified that fibrinogen is a protein, specifically a clotting factor, which are responsible for the aggregation of the red blood cells. In this work, we applied the hypothesis that higher fibrinogen levels leads to more severe red cell aggregations. So before we go to the simulation part, I'm going to show the red cell modeling techniques that we employ in the first part. We use a method, namely the dissipative particle dynamics, which are characterized by where the interparticle force are characterized by the summation of 3 different parts. One is the conservation part, second is the dissipative part, and third is a random part. This is a mesh-free and coarse-grained particle-based method that we employ in a lot of our later red cell simulations. And specifically to simulate the red blood cells in diabetic blood and the normal blood, we employed a model based on this that was previously validated in our colleagues' previous works. Additionally, the diabetic red blood cell model is recently validated by Chang using the optical tweezer test and micropipette. The diabetic red blood cell is characterized by higher surface to volume ratio and doubling shear modulus than the normal red blood cells, according to a systematic peer review by Chang. Okay, so to model the cell-cell interaction for red blood cells, we extended the cell-cell interaction model previously validated by Fedosov for normal red blood cell to both normal and diabetic red blood cells. In particular, we used an adhesive part of the Morse potential to represent the cell-cell adhesion and use the repulsive part of the Alger potential to prevent the cells from overlapping with each other. To address the different levels of aggregation strengths, we built these 3 different categories of red blood cells, where the blue vertices represent those particles under Morse plus Alger cut potential, while the red vertices only have the Alger cut potential. By varying the proportion of the blue and red vertices, we were able to build cells with different levels of adhesion strength. So the first step of our model construction is that we're trying to quantify the hyperparameter denoted highlighted in the previous slides in the Morse potential. And specifically, we use existing doublet breakup experiments by atomic force microscope and the optical tweezer. In the atomic force microscope test, the top cell of the doublet is pulling perpendicular to the contact surface of 2 red blood cells, while in the optical tweezer test, the top cell is pulling along the contact surface of 2 red blood cells. We found the critical force to break up the already adhered doublets are different using these 2 experimental techniques. In particular, the force in atomic force microscope can be 1 order greater than that in the OT test. Also, the critical force to break up doublets in different fibrinogen concentration level are different as well. We experiment with different the amount of blue vertices coverage to generate a similar measurement compared to different experimental resources. And finally, we came up with the exact denoid at a specific level. Okay. To systematically study the doublet disaggregation through microchannel, we selected 3 typical patient sample, and we identified the percentage of rouleau of different lenses are varying from patients to patients. And we also realized that this is positively correlated to their fibrinogen concentration level. Therefore, we constructed patient-specific red blood cell models based on direct observation from our microfluid experiments. First, here is how we construct patient-specific red blood cell models. First, we randomly chose 10 frames of the time-dependent snapshot from each patient. We count the number of singlets, doublets, and multiplets within the region of interest. Then we calculate the percentage of each type of rouleau for each patient. See the figure in the middle. To demonstrate the overall cell-cell adhesive strength for patients, we plotted the average interactive vertices ratio of patient-specific Reposal models implemented in the simulation. To validate this experiment-informed RBC models, we compare patient-specific rouleau breakup rates at the doublet level, shown on the movies that was moving previously. In experiments, we keep track of 20 doublets and record the number of doublets that are fully separated before they exit the region of interest. See the unshaded bar in the rightmost figure. On the other hand, for each patient, we simulate 24 patient-specific doublets passing through the microgates and calculate the percentage of fully separated doublets over the total amount of doublets observed. See the shaded bar in the rightmost figures. These simulations and experiments results agree well with each other, as suggested by the bar plots, confirming that the distribution of rouleau length is an important indicator of its corresponding doublet breakup dynamics. Okay, how about the multiplet disaggregation dynamics through the microchannel? From our microfluidic experiments, we noticed that the alignment of a long rouleau with respect to the flow direction plays a key role in its breakup pattern afterwards. To probe this phenomenon qualitatively, we carry out simulations on two 10-cell rouleaus, representing a long rouleau passing through the microgates. So the first rouleau entering the microgates with an angle respect to the flow direction, while in the second rouleau, it enters the microchannel along the flow direction. Play the movies. The snapshots show that these two rouleaus experience distinct collision with the microgates and hence exhibit different breakup patterns. The rouleau with inclined center line breaks up into several triplets and one quadruplet, while the rouleau having its center line along the flow direction split into two doublets and the two triplets. We performed this simulation for a couple of different initial setup, and we gathered a histogram of these different histogram of the later breakup counts of the diabetics, of the doublets, multiplets, and singlets, and generate these two distribution for these two different setups. We think that our simulation of this long rouleau breakup pattern could guide the design of microfluidic device and improve the efficacy of separating aggregatable cells without break up the cells. Okay, here I'm going to talk about the second part where we investigate hemodynamics in thrombos formations. So a thrombus is a blood clot in the vessel, which occurs when the blood vessel is injured. It involves 4 different stages. One is platelets moving close to the vessel wall through imagination. And second is coagulation factors transport is triggered by a series of chemical reactions. And third, the marginated platelets are then activated and change from ellipsoidal shape to fully spread cells and adhere to the vessel wall. And the last stage, the adhered platelets recruit free activated platelets, forming platelet aggregations. So compared to normal blood, we found that diabetic blood not only have higher fibrinogen level, but also having but also have larger platelets and different red blood cells, as shown in the previous chapters. So there are two different pathways for the coagulation cascade mentioned in the previous step involving complicated chemical reactions. And these two pathways are namely the intrinsic pathway and the extrinsic pathway. While the intrinsic pathway is initiated by the surface contact, the extrinsic pathway is initiated by tissue damage. Since patients with type 2 diabetes suffer from chronic formation, in this work, we specifically focus on simulating the coagulation cascade initiated by the tissue damage. So how we represented the coagulation cascade kinetics using the ordinary differential equation of advection, diffusion, and reaction. Coupled equations. To incorporate the systems of ODEs into our framework of dissipative particle dynamics, we employed transport dissipative particle dynamics developed by Lee in 2015 to model the changes of chemical concentrations. In addition to DPD, in transport DPD, every particle additionally carries a flux term consists of a Fickian flux, random flux, and the source term representing the chemical reaction. So here is a simulation setup that we employed in this work. We modeled the cell dynamics inside the rectangular channel mimicking the size of a vein. The geometrical and the mechanical property of the red blood cells for normal blood and diabetic blood follow this this represented in this in the last chapter. Here I'm going to specifically introduce the modeling of platelets. So we modeled the platelets with ellipsoidal rigid particle, where the shear modulus and bending rigidity are the same for platelets in normal blood and that in diabetic blood. The only difference is the size of diabetic platelets is doubled compared to that of the normal platelets. To simulate the effects of tissue damage and initiate platelet activation, spatial varying concentration level of subendothelium bond TF7A complex is prescribed at the site of the injury. Also, to characterize the platelet adhesion to the vessel wall, we employ a stochastic bond formation and rupture formula as shown in the slides. So here are some results that we obtained from the simulations. On the top, we visualize the cell dynamics along with the thrombin concentration, which are highlighted by a really small bar near the wall at three different sequential time points. We note here that while thrombin propagates similarly fast in the channel for both diabetic blood and normal blood, on the right-hand side, the diabetic blood has more platelets adhered to the injured side. We also compare the concentration contour of another factor, fibrin, which is very important to evaluate the strength of the thrombin formation. These results suggest that the diabetic blood develop a higher concentration of fibrinogen on the cell-free layer near the wall. Also, we run each, here we show some statistics of the platelet adhesion. We run each simulation for normal and diabetic blood for 5 different times and count the adhered platelets as well as the formed bonds. These results suggest that at the steady state, the number of adhered bond doubled in diabetic blood compared to that in the normal blood. And about 25 platelets is adhered to the endothelial wall, while only 20 platelets is adhered to the wall, to the wall in normal state. This altogether suggests that diabetic blood shows higher platelet adhesion compared to normal blood. So here is a brief summary of what we have presented. We have shown that fundamental models for in silico simulation on blood cell dynamics for patients with diabetes. These models elucidate and quantify the mechanisms modulating the abnormality of cell-cell interactions and thrombus formation in diabetes, whereas glycemic control is still a major goal to manage cardiovascular diseases. Okay, here we're going to show the second part. We'll focus on the data-driven models for glycemic predictions. The first project I'm going to talk about is the short-term glucose prediction using deep learning. So physicians have established this gold standard to help patients maintain the glucose stability. The gold standard covers both long-term factors and short-term factors. Short-term factors colored in red. This altogether require the prediction algorithm with the following properties. First is that the algorithm must be fast enough for the patient to react to any unfavorable states. For example, as we mentioned, hypoglycemia will induce a coma. It is very necessary for the algorithm to inform the patients before the blood glucose drop to 70 milligram per deciliter. Second is that algorithm should be accurate enough so that not to mislead the patients. For example, you can't confuse hypoglycemia with hyperglycemia, which will lead patients to do the opposite actions to alleviate from the symptoms. Third is that the algorithm should be patient-specific to address the different characteristics among patients. However, with all these requirements, we are faced with the following challenges. Because the requirements of patient-specific and being fast, we are always faced with a small data set. And in real data set, the data imbalance always exists because the collected data usually have far less hypoglycemia versus and hyperglycemia samples than the normal glycemia samples. So we formulate the problem as follows. We use a historical 30 minutes continuous glucose monitoring data as the input, and we aim to predict the blood glucose level in the near future. For example, shown in the figure, a prediction horizon of 30 minutes. Depending on the resolution of our classification task, we can have two different classification tasks, namely the binary classification where we predict if patients develop hypoglycemia or not, and in three-class classification where we predict whether patients develop hypoglycemia or stay in normal glucose levels. Also, a brief introduction on data set that we use is that we have 83 hours of blood glucose per patient and around 1,000 samples per patient. And the input vector is of dimension 7. So before we go into the results part, I want to get everybody in the same page by introduce a few things about artificial neural networks. So apparently not only the name, but also the structure of artificial neural networks are mimicking the natural neural networks in our brain. On the left, you can see an illustration of neuron in our brain. On the right, you can see an example of the artificial neural network actually the vanilla one, which is the fully connected feed-forward neural networks. So in artificial neural networks, the input values are fed into the first layer after some weighted sum, then pass into an activations, then pass into the nonlinear activation functions. And this process goes on until the last layer, where we convert the vector to a desired output shape. Depending on the number of hidden layers, we have shallow networks with a few hidden layers and deep networks with dozens of hundreds of layers. In the past few decades, many research fields have witnessed huge advances and benefits brought by deep neural networks, especially the computer vision and time series analysis, which is a similar task that we are studying today. So to tackle the problem of small data set, we developed the following model shown on the left upper panel, consisting of a feature block and a FNN block, where by varying the feature units in the feature block, we create 3 different models, namely the iron model consists of gated recurrent units, CNN model consists of gated convolutional sequence-to-sequence units, and the self-attention network using the self-attention units. We also implemented 4 different transfer learning methods on 40 type 2 diabetic patients in our data set. And for each patient, namely the target patient, we carry out the following training step. First, we train the whole model using all other 39 patients' data. And the second, we fine-tune the model using different transfer learning method on the earlier part of the targeted patients' data. And we finally evaluate the performance of our model on the later part of the target patient's data set. So here I'm going to show the accuracy of our algorithm. The results suggest that more patients' own data leads to higher accuracy as you can see by increasing the axis, like the axis as the number of x-axis increase, the corresponding accuracy also increase in each subpanels. And among these 3 models, CNN and SAN achieve higher accuracy compared to the RM model. Also, we also identified that pre-trained model, transfer learning 1 and 2 are normally better than the last transfer 3 method. However, by close look at our data, we found some caveats induced by the imbalanced data set. But I'm going to show how we are going to tackle this problem. As we observed from the data set, that the number of hypoglycemia sample is far less than the number of not hypoglycemia sample. This will lead to classifier which blindly classify model input to make majority label and leading to the desirable algorithm lacking sensitivity for hypoglycemia sample, which is actually the priority of our prediction task. So to encourage the neural networks to learn more about the hypoglycemia sample, we perform 4 different minority data augmentation techniques. That means we will increase the number of hypoglycemia sample in our training data set. These 4 techniques are oversampling, which by repeating the existing minority sample in the training data set. Second is a Gaussian noise, where we add additional Gaussian white noise to the minority data to create more new minority samples. And the other 2 are time gun and mix up some modern techniques that I'm going to show in the next slides. So in the time gun, we take in, so first I'm going to show the algorithm of the time gun, how we generate the minority sample. So we take the minority sample and chain the time gun with these samples. By validating using the Tesny plot shown below, we will then use the trained gun to generate more new samples. And the mix-up, which was proposed by Zhang in 2017 recently, is a very elegant and neat method where you take two minority sample, namely sample 1 and sample 2, and you do a very direct interpolation between these two samples to generate the new data set, a new minority sample. Sorry. So here is the result of these data augmentation techniques. So specifically, we only show the binary classification because that's the top priority, and the result suggests that more minority sample indicated by the increase of minority data fold in the x-axis leads to higher sensitivity, while decrease positive predictive value. And among these 4 data augmentation techniques, Gaussian noise, time gun, and mix-up have increased sensitivity when more minority data is added into the training data set. Specifically, compared to Gaussian noise and mix-up, the time gun method shows higher robustness by having a small standard deviation among these metrics that's being examined. Altogether, we found that data augmentation brings to the model with new information about the prediction task. We also test our model performance on another real-world data set for type 1 diabetes, namely the Ohio T1DM dataset. On the left, I'm showing a few examples of the patient's blood glucose monitoring in Ohio T1DM dataset, while on the right, we show the patient's blood glucose level in our datasets. Luckily, our algorithm outperformed some existing algorithm on Ohio T1DM dataset. Here we compare the performance of our model on regression task for prediction horizon at 30 minutes and 60 minutes. Specifically, the peer results we shown here only take into account only use the blood glucose level as input vector as we did in our work. So we outperform other existing algorithms in terms of mean absolute error for both prediction horizons, and maintain the second best in terms of the root mean square error. In the table below, we compare our binary classification results with that of Bevan, because apparently their work was the top among the first tables, which and the results suggest that our model outperformed the model by Bevan et al. In terms of accuracy, F1, sensitivity, and negative predictive values. Specifically, the sensitivity of our model is almost 10% higher than that in their works. Okay, in the next part, I'm going to introduce some of ongoing work that we are working on in terms of long-term hypoglycemia detection. Before we show that some results on short-term glucose management, but how about long-term glucose management? In fact, how can we learn the pattern of a good glucose management plan in general? And we also want to ask, because we show that type 1 diabetes in the previous project, is there any difference among type 1 diabetes and type 2 diabetes in terms of long-term glucose managing. So for diabetic patients, usually they have to discuss the following like lab tests: eating habits, glycemic control, physical examinations, and medicines with their doctors. And this also bring us to the new form, another form of the data set that we are interested in learning, which is electronic health record, short for EHR. So here we found that, according to the literature, we found that although improved glycemic control reduces the rate of long-term cardiovascular diseases in patients with type 1 diabetes, whether the patients with type 2 diabetes will be benefit from a good glycemic control was unclear. To investigate this problem, NIH initiated action to control cardiovascular risk in diabetes, namely a core trial, which randomized 10,250 patients with long-standing type 2 diabetes to either intensive, namely glycated hemoglobin level lower than 60%, or standard glycemic control, where the level are maintained between 7 to 79%. In this trial, researchers collect the following information from the patients. For example, the demographic data, medical history, medication, diet, physical activities, physical examinations, and lab tests. So, as we mentioned, that this is our electronic healthcare record, health record data, which follow the characteristics shown in the slides. First, these data are unstructured, while the questionnaires are free text. Lab measurements can be real valued, and there are also images to help the diagnosis for doctors. And second, the missing data is frequently seen in EHR datasets, which results in the sparse measurement. Thirdly, we will probably be faced again with the same data imbalance as we mentioned in the last project. Okay, here we trying to investigate the hypoglycemia detection problem by formulating the task as the 1-year severe hypoglycemia detection. We use the patient's electronic health record in the first year as a model input features, and we aim to predict the occurrence of severe hypoglycemia events in the next year. Where the severe hypoglycemia is defined as a combinational results of whether the patient's glucose level dropped to below 50 milligram per deciliter, and also requested hospital admission and or medical assistance. And to address some of the challenges that we mentioned in the previous slides, as for the missing data, we performed a forward imputation given the time-dependent feature of the dataset. Okay. So given the clinical, like by discussing with our collaborator in physician collaborator, we realize that the related risk factor measurements and medication follow two different features. Like some are statistic feature and some are dynamic features where it varies among times. Since the time-dependent features are not measured with the same frequency from each other, we encoded the sequence of dynamic feature with the mean and the standard deviation of the sequences. Also, we identified that we have a large amount of unlabeled data set from this EHR, because not every patient have a record in in the outcome sense, but their input measurements, for example, those medications, metabolics are still available for us to provide more information into our model. So I'm going to introduce the algorithm that we're going to employ in this project. Given the unstructured nature of our data set, we developed a multi-view learning machine learning algorithm, where the high dimensional input feature are divided into different views depending on their characteristics, guided by our clinical collaborator. What's more important is that we also consider two different cases. In one case, we do not use the unlabeled data set we mentioned, and in the other data set, we will try to incorporate the unlabeled data set. For the multi-view learning without unlabeled data set, we first separate the high dimensional input into different views. For each views, we train the model on the training data set and predict it on the test data sets using the trained model, just like we regularly do. While in the last step, we combine the model prediction in different views and obtain the final label for the input feature. For multi-view learning with unlabeled dataset, first, for each view, we train the classifier with labeled dataset. Second, as we did in the case without unlabeled dataset. Second, we generate pseudo labels for unlabeled dataset and supply these pseudo labels into the original training dataset. And the third and fourth step are similar to those in the multi-view learning without unlabeled dataset. So here I'm going to show a preliminary data we found by employing the algorithm we mentioned. Whether using or not using oversampling and using or not using unlabeled dataset result in very similar result. All this together show that all models examined in this project have relatively high negative predictive value and the specificity. Among the algorithms, logistic regression with oversampling and unlabeled dataset has highest sensitivity, which is highly favorable in the clinical point of view. However, we found that it's really hard to have a classifier perform equally well in all these metrics examined, probably because the data imbalance and high dimensionally data leads to a complicated decision boundary in our task. So this is still ongoing. We're trying to tune our model to achieve a better results. So here's a summary of the presentation. With the past slides, we have presented fundamental models for short-term glucose prediction and some results for long-term hypoglycemia detection. We believe that this model could help patients identify useful glucose changes and gain a beneficial lifestyle. So the future work of my research will be to join the efforts presented to better manage diabetes and related complications. Specifically, we want to use the power of big data to provide data-driven models, which can quickly provide patient-specific model inputs. By integrating simulations at different scales, we can eventually build a digital twin, which can provide patient-specific prognostic predictions and eventually improve the quality of life for patients with diabetes. Okay, here's the last slide. Thank you. And these are some references of my work. Yeah.
Thanks, Yishan, for the wonderful seminar, and it's very comprehensive talk. So if our audience have question, you can directly unmute yourself and ask a question to Dr. Deng directly.
Hi, Yishan, this is Xu. Yeah, it's a nice talk. I have a question on your second part of your talk. In the modeling thrombus formation in normal and diabetic blood, you made a comparison between the bloodlet adhesion. The blood adhesion between healthy blood and diabetic blood. You mentioned that you use different mechanical property and the cell volume for normal and diabetic bloodlet. My question is that whether you change the fibrinogen concentration at the same time as the high level of fibrinogen level have been reported in diabetic with vascular complications.
So you mean it will be, by combining the platelet shape change as well as the fibrinogen level, we will, it's not clear which one is contributing more.
Yeah, the fibrinogen level, or just like another adhesive protein, just like VWF, may play a role in the thrombus formation.
Yeah, I think that's, I hope I understand it correctly by repeating your question. Is the first question was about, is this increased adhesion a result of both platelet geometry as well as the fibrinogen level, right?
Mm-hmm.
Yeah, we're trying to mimic the most realistic situation. We didn't do the systematic study on like which factor, like the separated each factor and analyze. I think that will be a good thing to look at too.
Okay. Thank you.
Okay. Thanks, Xue for the interesting question to connect the biochemical concentration level to the deformation of the cells, right?
Yeah, because in the last slide, Yishan just mentioned that in the future direction, she wants to build just like a patient-specific model, just by combining the data-driven data. Yeah. So I think that.
Okay. No, do you have a question?
Yes, I do. So for the multi-view, the learning in the second part. Yeah. So basically in the multi-view learning, you split the input features, let's say, into different groups, and for each model, you only use one portion of the features. Then what's the advantage of this method, let's say, compared to, let's say, random forest? In random forest, we also, each time we also use a portion of the features.
I didn't compare with random forest. The flexibility of this setup is that you can use random forest with this.
What's in general, let's say, compared to other methods, what's the main advantage of this method?
So you see that the classifier are like put as a box. So you can use different classifier depending on the different feature of the view. Like sometimes you can use, for example, you can use logistic regression in classifier 1 while using random forest in classifier 2. You can like choose the best among them. And I don't know if random forest and also random forest is a ensembling method, right? So it may be more time consuming, I guess.
Or is this method mainly developed to prevent overfitting or?
Yeah, I think overfitting is one thing, and it's just to incorporate the clinical understanding into the model, I think, because by separating the features from each other, you are preventing the contamination because of the features mixing up.
Oh, I see. Oh, so how do you separate the features here? It's not random, right? Oh,
it's not random. It's by the clinical guidance.
Oh, I see. Okay, so manually have this some intuition to separate features. I see. Okay.
Yes, exactly. Yeah, it's like it's not a feature selection, but it's like a feature separation by clinical advice.
Got it. Yeah. Thank you.
Sure. Thank you for the question.
Okay, any other questions?
Good morning, Yixiang. This is He Li. First, I want to congratulate you for this excellent work. It's amazing you can achieve so many results in such a short time period. So actually, my question is also on this slide. So you have a you have a static feature, you have dynamics feature. So when you input them into the neural networks, are you using a different type of neural networks? In the next slide, you show the overall architecture of the network. Yeah. So for this view 1, view 2, are those like kind of a different type of neural network to read the different types of data?
So I want to mention it's a more like thank you for the question, and it's more like a abstract model. There is no neural network. You can definitely use the neural network as the classifier 1 or 2 or 3. You can replace the yellow blocks with neural networks. For no problem. The idea here is that we are very flexible in the classifier. It's not restricted to the neural networks. Does that make sense?
So this X1, X2, X3 can be just different properties. They can be either static or dynamics, right? This is what you want to show here.
Yeah. So for example, the view 1 can be a block shown in the static feature, while U2 can be also another static feature, another group of static feature that is clinical meaningful that they should gather together.
Okay.
Yeah.
So do you have an estimation on how much data you need to train this very complicated structure of this neural network?
It's not a neural network, and the interesting part is that if you do not have all this data, that's fine. We just take whichever we have and chain the classifier because they are independent from each other. You can even have only one block of features and you want to chain this network, that's fine. But not network, sorry. It's not network. It's not network. It's just a framework that incorporate everything.
Oh, okay.
Yeah, it's like usually if you have high dimensional data, you want to do a feature selection, then input into a sole owning classifier and tell you the output, right? But here we are more like generals in that we take all the feature, but we group them into different ones and chain different classifiers while we integrate all the results together to make a decision, like another ensembling. It's like separating. Yeah.
Okay, thanks, Scott. Also, my second question is for the long-term prediction of the glucose level. Like, for example, you want to predict the patient for the next year. So how do you, maybe I missed that detail, how do you handle the noise like happened in this during the next year? because the patient may have different some accidents, or they may have some surprising visitor from out town, and they have a very good meal, and which cause the glucose levels like spike of the glucose level.
Okay,
Like
so I want
the
to
other
start.
day, like last week, I know Dr. Lulu have a surprising visit by his one of his friend. They go to a very good restaurant, so this may cause some spike on the glucose level, on his glucose level.
Yeah, I mean, that's an interesting question, but I mean, for here, like for example, I'm showing here the numbers are the glycated hemoglobin level, which only changes in like frequently measure couple of months. I remember if I remember correctly, it's measure every 3 months, suggested to measure every 3 months for patients. So it doesn't change that much. Like we don't take the blood glucose level in our severe hypoglycemia detection, but rather we take some like more constant variables, right?
So basically, you assume that the lifestyle of the patient does not change in the next year. So then you can. So basically,
I think 1 year probably. I mean, the lifestyle in 1 year probably won't change that much. And for the feature of glucose, blood glucose that you mentioned, that's consistently changing over time, we do not consider that because that's not a good indicator of the severe hypoglycemia. So all these features were actually pre-selected by the doctors as well.
Okay.
Yeah.
Okay, thank you very much.
Okay,
No
so
problem.
any other questions? So Yishang, I have one question about you try to previously you introduced you try to learn from the small data, but if the data set is too small, you are trying to use a mix up, do the interpolation between two data sets to generate new data for training.
Mm-hmm.
So
yeah,
have you considered to use some, for example, the clinical data is not enough? Do you consider to introduce some modeling from simulation part to enrich the training data set rather than do the interpretation between the clinical data? Or currently you cannot combine modeling data and the clinical data?
Yeah, I'm not sure I understand it correctly, but
I think Jane's suggestion is you can do some simulations, right? You can have simulated data.
Oh.
Either OD or DVD, whatever.
Yeah. I mean, the real data set is, I mean, the highlight of my research project, I would say. And I'm happy to use some synthetic data in the future work because that's a powerful tool to generate the data set. Yeah, for sure.
Okay. Okay, thank you, Yishang. Then
Sure, thank you for the invitation.
So if we have other question to Dr. Dan, you can contact her directly. So her information is posted on our CFSM website, so you can have her contact information directly. Okay, then we thank Yishang for the wonderful talk. We'll end here. Bye-bye.
Bye-bye.